since we will be using the permutation group extensively, it is useful to define something from within permutation group first, which is called cycle structures. So we are going towards defining conjugacy classes. Maybe we write it down first and then no, but it requires the proving and so on. So we can do it in either order. Let's do the conjugacy classes first. It's a very general idea and it requires some proving. If you find this discussion too abstract, then we will immediately be seeing examples of this in terms of the permutation group. We can also motivate it in another way. So one motivation was like the which one did we say, not ammonia, methane. Ammonia has similar thing, but it has different structure. Okay, so methane molecule, there are 4 equivalent axes joining H and C. The other way of thinking of conjugacy classes is what we call similarity transformation in linear algebra. Well, I apologize a bit here because I am talking almost like a mathematician. For mathematicians, examples are more things from within mathematics. Ideally, we should have some, concrete thing to give in terms of, but let me say I am drawing on what you may be already familiar with or what is a little more familiar to us already, which is where a linear transformation acts on a vector, okay, a matrix acts on a vector. So action of a matrix on a vector, which is a linear transformation on, so suppose we have m times x equal to y, and now if we think of this geometrically, then x has the notion of a vector which we can assign a physical meaning as like a position space, and m is some kind of a rearrangement of its components. But if it has to have a independent meaning, then we can think in terms of the bases, and the action is like changing the bases, okay, changing the basis in terms of which we are expressing this. So to cut long story short, let me just tell you what I have in mind. Suppose we multiply it on the left by some transformation S, which is also a matrix, and we will say non-degenerate invertible matrix. One that has an inverse. Now what we can do is we can rewrite this as SMS inverse on Sx equal to Sy. Okay. So if the vector space is transformed using S into from V to V, I mean it's a internal transformation, automorphism sometimes called, then correspondingly the matrices have to be transformed by SMS inverse. Okay. So transforms as SMS inverse. That is the statement. Then the geometric meaning is preserved. It's just that you went to some other frame which was S times the original, but physically what is happening is the same. So this is meant by a conjugacy relation. So this is exactly what we are going to propose for group elements, because group elements, although we are writing them as if they are an independent algebra, we know that secretly they are always going to be realized as operations on something. So they are actually in the class M, group elements. So we propose for group elements conjugacy relation. We say that x and y belonging to G, I jump to some other symbols, are related, are conjugate to each other, provided there exists a G belonging to G such that G x G inverse is equal to Y, and we can check that this requirement is a equivalence relation. Okay, and I am sure you have already started doing it in your head, checking why this is true. Can you write it down? What are the things to be checked? So we can check that reflexivity holds, G equal to E. Symmetry, so G inverse is the required element, and for transitivity suppose G1 x G1 inverse equal to Y and G2 y G2 inverse equal to Z, then we can see immediately that G2 G1x G1 inverse G2 inverse is equal to nothing but G2y G2 inverse is equal to Z, right? Because this is nothing but Y. But then I rearrange this to write it as G2 G1 on X and G1 inverse G2 inverse on X, G2 inverse equal to Z, that is to say G2 G1 X G2 G1 inverse, because G1 inverse G2 G1 inverse will be equal to G1 inverse G2 inverse, and that is equal to Z. So that verifies transitivity. The beauty of this proof is that it uses up all the properties of the group G. Group G has to have the identity element, okay. It has to have inverse, so that inverse of inverse is itself, and associativity is very crucially used here. If I have G2 times this, then it becomes G2 G1. So all the closure, associativity, identity and inverse are all used for proving this equivalence relation. The result therefore is what you would have expected. This conjugacy relation is an equivalence relation, and therefore it divides the group G into conjugacy classes. Now note that the conjugacy classes are not of the same size, they are all different, but of course you can recover the whole of group G as union of the conjugacy classes. The element identity is in its own equivalence class, is its own conjugacy class, because it will never get related to anything else. E will always remain related to itself. If you put G, E G inverse, you will get back E regardless of what G you used. So E can never be converted into anything else by this kind of transformation, and so E will always constitute its own. So size of conjugacy classes need not be same. Sizes is what I mean. Sizes of the different conjugacy classes need not be the same. Identity element remains in its own equivalence class, a conjugacy class. More generally, if you have an abelian group, then in an abelian group every element remains in its own conjugacy class, because in an abelian group any operation like this, everything commutes, so x will remain x regardless of what G you use. So in an abelian group every element is in its own conjugacy class. But we will see that for the non-abelian groups the conjugacy class proves to be a very powerful idea, because you can in fact think of only the members from each. So you can think of much fewer elements instead of having to think of all the elements. All the elements belonging to the same conjugacy class you can treat as essentially one. One representative from it will be enough for thinking whatever you are trying to think. Also we will see some very useful technical things which have to do with the representation. When they get represented, also there is a uniformity in the representation. So now we will see an example, unfortunately as I say a technical example of conjugacy classes in the case of permutation group. So let us return to the symmetric groups. For this purpose we first develop the idea of cycles in a permutation group. Quite simply put, let us start with an example. Suppose we have S8 okay, and I pick 3571 2846. So this is some element of S8. It says the original order is permuted into this order. Now we see what happens here is that 1 goes into 3, but 3 goes into 7. And 7 goes into 4 and 4 goes into 1. So we have this sequence: 1 goes to 3, goes to 7, goes to 4 and goes back to 1. So this is like a sub permutation on a subset, and this thing did not involve any of the other elements. What you can see is that if you square this element, take square of this element, multiply it by itself, all it will do is it had slided 1 to 3 first, now it will slide 1 to 7 and it will slide 3 to 4, okay. But it will basically slide these among themselves. If you take higher powers of this particular element of S8, all that will happen to this cycle is that the cycle will continue within itself, okay. It didn't touch any of the other elements, so let us see the fate of the others. So 2 went to 5 and 5 went to 2. I am sorry to color it all up, okay. So 2 goes to 5, but 5 goes back to 2. So that is another cycle. And now we have covered 1, 2, 3, 4, 5 and only 6 and 8 are remaining, and obligingly they are going into each other. So 6 goes to 8 and 8 goes into 6. So we have one more cycle which is 6 goes into 8 and 8 goes into 6. So we write the cycle notation then is to identify such cycles and then only write one, 3, 7, 4, 2, 5 and 6, 8. This is what we write. So the same element, if you want to call it, let us call this pi 1. We call pi 1 equal to this. So pi 1, of course the standard way of writing is this long way, but we can also write it out simply by its cycle structure. It is the element that is going to send 1 into 3, 3 into 7, okay. So this is another way of writing it. And you can see that if I square this element, what will happen? It will just slide these among themselves again. 2 has gone to 5, 5 will go to 2, again 2 will go to 5, 5 will go to 2. So higher powers of this will maintain the cycle structure, it will not alter the cycle structure. So in fact that is the, I wrote is an example, but the more formal way of defining cycle structure is to define it like this. You say that take an element pi of the permutation group, and if you find that pi to the power some pi, and look at one of the objects, its action on one of the objects, and then look at the action of higher powers of pi on that same object. Because the whole set is exhaustible, it is finite, at some point pi to the power r must return that element to itself. That is called the size of the cycle. It's called cycle of the pi then has contains one cycle of size r, and then you take another element which is not in your first cycle, again take higher powers of pi in it, you will find a shorter or longer another cycle. So the more formal way of defining actually relies on the fact that the same element pi raised to higher power is going to only cycle the elements of one cycle among themselves, and therefore bring them back to original order at some power r, and that power r is actually the size of the cycle. So if you do pi 1 squared, it is going to bring 2 5 back to 2 5 5 2 back to 2 5. So this is cycle of size 2 because pi 1 raised to power 2 returns this pair or this list of elements to itself. This is cycle of size 2 because pi square is going to do this. This is cycle of size 4 because you will have to raise pi to power 4 to restore this set of elements to their original order. So this is how actually a cycle is formally defined. Okay. So we already have an intuitive idea what a cycle is, but what we say is that given pi, consider its effect on a specific member of the what is the space? The base space, not the base space of the, what is it called? Carrier space, thank you. Of the carrier space pi of, let us say 1, for example pi of 1, then if r is the smallest number, such that pi to the power r of 1 is equal to 1, then 1 is said to belong to a cycle of size r. So in general pi will split up into contain several cycles of sizes r1, r2, etc., starting with distinct members of the carrier space. So, the important fact we are moving towards proving is that once you represent elements of the permutation group as in this cycle notation, what you will find is that under conjugate transformation the cycle structure does not change. So, let me write it at, okay, so we shall see that. Conjugacy classes in Sn are subsets with same cycle structure for its elements. So, to begin with, and just to get a little familiar with this whole thing, let us take an example where we are not actually going to do conjugacy relation, but just multiplication. So, our example is S8, pi 1 as before. Maybe I should try to be a little compact so that I can fit over here. Pi 2, so 1, 4 should be reached here. So, 2, 3, 4, 5, 6, 7, 8, 1, and so here what I have written on the previous page, which is 3, 5, 7, 1, 2, 8, 4, 6, and pi 2 has 2, 5, 6, 8, 1, 7, 4, 3. So, first, what are the cycle structures? So, rewrite the elements in cycle notation. Sorry, 8, 3, 6, 7, 4, 8. In fact, yeah, this is the long cycle, and 8 goes back to 3. So, that is what. So, this is a element with 3 cycles, and this has only 2 cycles. There is one long cycle in that. Now, suppose we take pi 1 O pi 2, pi 2 O pi 1 first. How do we do this? We want to be able to cancel this with this. So, pi 1 I write over here. Now, pi 2 is here. What I do is I write out pi 2 in such a way that the top row is exactly in same order as this row, and transposing the corresponding bottom element with it. So, I need 3 first, 3 has 6 below it, then I need 2, 2 has 5 below it, 3 has 6 below it, 4 has 5 below it, 5 has 6 below it, 6 has 5 below it, 5 has 6 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 be then I have sorry 3 5, so 5 is 1. Let me write it out here, 1 2 8 4 6. Okay, so I write this row exactly over here, and then here I pick the corresponding columns. So 3 goes to 6, 5 goes to 1, 7 goes to 4, 1 goes to 2, 2 goes to 5, 8 goes to 3, 4 goes to 8, and 6 goes to 7, right. Now we can cancel out the upper row here with the bottom row here, and it produces the equivalent permutation, which is 1 2 3 4 5 6 7 8 6 1 4 2 5 3 8 7. Now what is this in cycle notation? Well, it is 1 6, 6 goes to 3, 3 goes to 4, 4 goes to 2, and 2 goes to 1. So that is one cycle, and now 1 2 3 4 have been exhausted, so 5 remains 5, then 6 is already used up, and 7 and 8 get exchanged. Sometimes in cycle notation this 5 is not written, what is not being changed is sometimes not written. So in fact often not written. In cycle notation. So they will write only the non-trivial cycles. Whatever is not in the list of listed cycles is not changing. That's all it means. Okay. I also wanted to make a comment here that I introduced transpositions by just saying you exchange pairwise. I had to do a lot of things like this. Now that we have defined cycles a little more formally, I can tell you that a transposition is essentially a cycle of size 2. Okay. So it makes it a little more rigorous what we meant by transposition, and we can check that every possible cycle of any size can be written as a product of transpositions, two products of two cycles. So those things tie up with what we have been talking about earlier. Now, well, if we spend a few minutes more, then we will see something useful, which is do the multiplication in reverse order. So next, consider pi 1 O pi 2. So I hope you are enjoying this game. So pi 2 we write out as is. Now pi 1 has to be written, but before writing it I put this at the top. And then from pi 1 read off the corresponding columns. So 5 goes to 2, 6 goes to 8, 8 goes to 6, 1 goes to 3, 7 goes to 4, 4 goes to 1, 3 goes to 7. Now we cancel out the commons layout of the permutation, and so we get the answer 1 2 3 4 5, 6, 7, 8. Actually the 8 is picked so that it doesn't, if you take smaller thing, I mean you can work with 5 also, but sometimes it looks like accidental and you begin to repeat things, so it's better to have lot of elements around. So it becomes 5, 2, 8, 6, 3, 4, 1, 7. And what does that become in cycle notation? 1, 5, 3, 8, 7. That is one cycle. 2 goes to 2 and 3, 4. 4 goes to 6 and 6 goes to 4. Now what we observe is that, of course, pi 2, pi 1 is not same as pi 1, pi 2, they are different elements, but their cycle structures are identical. So the order of multiplication produce the same cycle structure. So this is going to be useful for proving that conjugacy classes all have exactly same cycle structure. Okay, so we will continue next time.